Hello everyone, I'm Martinus Bagus Wicaksono. I'm a doctoral student at Mechatronic Department Raja Manggala University of Technology, Tanyaburi. In this occasion, I would like to uh, present the understanding of PID controller. So in the first part, we would like to discuss about introduction to PID control. Here, the PID control is a control algorithm widely used in industrial control system to regulate the processes like temperature, flow, pressure, speed, and another processes variable. And this is used to achieve a desired set point here. In this PID, it consists of three terms: proportional, P, integral I, and derivative D, which work together to provide stable and efficient control. The first term is proportional. So here we will talk about the proportional term. In here, the proportional term produces an output that is proportional to the current error. So the difference between the desired set point and the actual process variables. Here, the larger the error, the larger the corrective action. This is the block diagram. We have set point here, and then this is comparator, and here the proportional controller, and then this is the process plan. At the end, we have the output, and from the output to the set point, we have branch name feedback. Consider we have a temperature control system of an industrial oven. The desired temperature here is 200 degrees Celsius. This is the set point. But the actual temperature is currently at 230 degrees Celsius. So here, the proportional term will generate an output signal that is proportional to the error here, which is 30 degrees Celsius. And we'll try to bring the temperature closer to set point by adjusting the control input. Here, it will adjust the heater power here. And gradually, the temperature will increase until it reaches the set point. This is for the proportional. Next, we will talk about the integral I. The integral term takes into account the whole sum of previous error and responds to the magnitude and duration of the error. It is used to remove persistent steady state faults, which is the proportional part cannot take into account. Here the block diagram of the integral and proportional, and here the set point, and then this is the proportional and integral controller, and then this is the plan, output, and the feedback here. So let's say we have the oven, industrial oven. So here, in the same temperature control system, if the oven has a minor error that causes it to constantly run 3 degrees Celsius over the set point, the proportional term may not remove this error. So the integral will accumulate the mistake over time and execute a corrective measure to gradually eliminate the error. So this is assisting the system in accurately reaching the set point. This is the test of integral. Next, we have the derivative, or d. This is not I, but it should be d. The derivative term takes the error's rate of change into account. By responding to the rate at which the error is changing, it anticipates upcoming error. So it will predict the upcoming error, the future error. It assists in reducing the system's reaction and minimize the oscillation and overshoot. So let's say we have here the level control in the tank. So in a level control system for a tank, if the inflow rate suddenly increase, causing the level to rise rapidly. So the derivative term will respond to this rapid change and reduce the control action to prevent the overshooting set point. So most practical control system use very small derivative time, or TG, because the derivative response is highly sensitive to noise in the process variable signal. So if the sensor feedback signal is noisy, or if the control loop rate is too slow, then the derivative response can make the control system unstable. That is the derivative. So in the next part, we will talk about the function of some parameters. The first parameter is rise time. Here, the function of the rise time gives an important information about the system's dynamic behavior and its capacity to adapt quickly to changes. A quicker initial response is shown by a shorter rise time, which suggests that the system is able to react quickly to disruptions, set point changes, or input variances. Here we have the sample here. Consider if we drive a vehicle with a cruise control system. So no matter how the driving condition change, the cruise control maintains a predetermined speed, or a set point here. So this is the car with a cruise control. In this context, the rise time describes how quickly the vehicle's speed adjusts when the cruise control here in this car is activated. So in the conclusion, rise time is an important control system parameter that helps engineer in fine-tuning the system's responsiveness to satisfy certain object, whether it's for obtaining quickly changes, reducing overshoot, or ensuring comfortable and stable operation. The next function is, the next variable is overshoot. So here, when a control system output exceeds the specified set point or target value before settling down, this event known as overshoot. So here, this is the overshoot. So the system output exceeds the specified set point here. This is the set point, 70 degree, but it exceeds here over than 70 degree. And it takes place when the system reacts suddenly to an input or set point change. Overshoot serves to provide information on the dynamic behavior or of the system, such as its responsiveness, stability, and potential for the oscillation. So you can imagine here control temperatures of chemical reactor. So the desired temperature is 70 degrees Celsius. This is the set point. The overshoot scenario would represent in this how reactor's temperature goes above 70 degrees Celsius before it settling. So this is the overshoot. The next variable is settling time. Settling time is the amount of time it takes for a system's output to get to and stay within a given range around the desired set point. So following the change in input or set point. So this is known as the settling time. It offers crucial information about how rapidly a system changes from its initial state to the steady state one. So here in this graphic, we have TS. TS is the settling time. Time that is take from of the system to stay within a given range around the desired set point here. So here the TS. This is the settling time. And next variable is delay. The idea of delay commonly referred to as time delay. Here, the delay used in control system to describe the amount of time it takes for an input change to be clearly seen in the system output. So again, we can consider as an autonomous vehicle that detect the obstacle here. This is the obstacle. This is the autonomous vehicle, and adjust its speed as needed. So in this case, the delay is the amount of time it takes for the sensors here to detect an obstacle in front of the autonomous vehicle here and process the data and send a signal to the vehicle's control system to slow down. Next parameter is underdamped. Underdamped is a dynamic system that responds with an oscillation during its transient behavior following the changes in input or set point. So it is said to be underdamped. So the system that is underdamped has a response that first exceed a desired set point and then oscillate around it before settling. So this is the underdamped. The next variable is overdamped. Here, the overdamped is a dynamic system. Is said to be overdamped when it responds to a change in input or set point by gradually moving toward the intended set point without any oscillations. Compared to a critically damped or underdamped system, an overdamped system is characterized by a slower response to the output here. So we can take an example of an automatic door closer here. If following a person passing through an entrance, this mechanism is intended to securely and smoothly close the door. Overdamping can occur when a person enters the door and then the mechanism reacts to that. It will close the door slowly until it perfectly closes without any overshoot. So this is the overdamp. Okay, this is the end of my presentation about the understanding of PID controller. Thank you for watching the video.